chemists were searching for patterns in their properties that might reveal a deeper structure. The properties of the elements were well known to the Russian chemist Dmitry Mendeleev, who wrote down their names and properties on cards and arranged them in order of their atomic weights. He noticed that the chemical properties had a pattern. They repeated at regular intervals, a periodic law. Mendeleev described his discovery. "I saw in a dream where all elements fell into place as required. Awakening, I immediately wrote it down on a piece of paper. Only in one place did a correction later seem necessary." The pattern showed that there were also some elements missing from the table. He left gaps for these, confidently predicting the elements germanium, gallium, and scandium, which were soon discovered. The modern periodic table is arranged not by atomic weight but by atomic number, the number of protons in a nucleus, ranging from 1, hydrogen, up to 92, uranium. The atomic number is equal to the number of electrons in the atom. Elements heavier than uranium are produced artificially. Henry Moseley developed an X-ray technique to measure the number of protons in the nucleus, and we have him to thank for essentially the modern version of the table. As the atomic number increases along successive horizontal rows, the chemical properties repeat in periods of 2, hydrogen and helium, then 2 periods of 8, lithium to neon, sodium to argon, and then 3 of 18. The table is more than a classification scheme. It reveals a pattern that is deeply embedded in nature and the structure of atoms. The periodic table is governed by quantum laws. The electrons in atoms spread out around the nucleus in what are known as atomic orbitals, which form shell-like structures around the nucleus. Atoms seek to minimize their energies, which is what happens when their electron shells are completely full. For example, the first atom with a full shell is helium, atomic number 2, the second is neon, atomic number 2 plus 8 equals 10, and the third is argon, atomic number 2 plus 8 plus 8 equals 18, and so on. These stable filled-shelled atoms are the chemically inert noble gases, which sit in the last column of the table. The different atoms are like letters of an alphabet, which combine to make molecules, akin to the words of a language. How many types of molecules are there? The English language has around 250,000 words in current use, all based on a 26-letter alphabet. The letter A is always an A, whether it appears in the word cat or in other words with completely different meanings, like bat. Similarly, each hydrogen atom in a water molecule is identical to those that combine with carbon to form methane, CH4, a molecule with completely different properties. In theory, it is possible to form billions of different stable chemical compounds by combining the elements of the atomic alphabet in different ways. The scale of matter. To fix ideas, it is important to appreciate the vast range of the length scales of matter. From the very smallest structures that we believe may exist to the largest, the visible universe, we cover a mind-bending range of 62 orders of magnitude in size, or 10 to the 62. This takes us from the quantum world of the smallest entities to that of the largest structures, which are dominated by the force of gravity. The largest structures range from objects the size of the Earth up to the clusters and superclusters of galaxies. Albert Einstein's general theory of relativity describes these huge structures and the space that they occupy. At the very small end of the size spectrum, the laws of quantum mechanics describe matter. At present, there is no complete theory connecting the quantum world and the gravitationally dominated world, and so the various theories of quantum gravity that have been proposed, which might bridge the gap, are not described here. Let's take an imaginary zoom lens and, starting from the human scale, zoom in to progressively smaller scales. To see the cells in your body, you would need to increase the magnification 100,000 times from the human scale. This is possible using wavelengths of visible light. However, light cannot be used to resolve structures smaller than its wavelength. The wavelengths of light are around